Hello, and welcome to another edition of Let's Talk SADS, live from Canada. I am your host, Dr. Shubayan Sanitani, or Dr. Shu, as most of the kids around here call me. And I'm delighted to be part of this relatively newly rebooted Canadian SADS program. And before I get started, I really want to thank uh, Aaron and Alice Lara at the American SADS Foundation and Michael Ackerman for giving us a boost and getting us started. And of course, Pam Husband, our executive director, who is the energy behind the Canadian SADS Foundation and has kept it going like an energizer bunny for all these years. So very excited and honored to be here. For those of you who may be new to these webcasts, and also to remind myself of why I'm here, this is really about informing our audience and people affected by SADS conditions, people who have relatives, people who are healthcare providers, and really bring us all together in a collaborative learning environment where I think I'm doing most of the learning because we have had some really interesting guests. Before we talk about our guest today, I want to do a little bit of my homework here because so hopefully you are seeing our Let's Talk SADS Live Canada. And really, as I say, this is a place where we come together to learn collaboratively from each other, from our experiences. And I'll remind you please feel free to put your questions and comments in the chat. We have Evan in the background managing all the tech, and we can handle your questions. We probably can't handle an essay about your uncle's nephew who has heart palpitations, but we'll try and give you some information back. So this week, I've been spending a bit more time on the SADS.ca website, which is in the process of being rebuilt. And I was very excited to see the new medical advisory board featured on there. And we're going to meet some of those guests later in the season. And also to remind ourselves of what SADS Canada really is about. So I reminded myself a little bit, and I forgive me for all this text on this slide, but really what we are doing is we're committed to saving the lives of children, young adults who are at risk for SADS conditions and sudden death, sudden cardiac arrest. And then I spent a bit of time thinking that, I haven't done any time really promoting these warning signs. So maybe on a more regular basis, I should remind people about these warning signs: fainting or losing consciousness, particularly during exercise or during emotional states. And certainly if you have a family history where young people have died unexpectedly. All too often we see these stories pop up on our social media feed or in the newspaper, or sometimes we even witness these tragic events. And just this week, someone in our clinic came to me and said they heard about someone that they'd known all their lives in their community. So these events do happen. They're thankfully quite rare. But our goal really is to help the families that are affected by this and never leave these families out there alone and wondering who, what happened, who looks after them. So that's really what we're trying to do here, in part through this webcast. Now, for those of you who've been tuning in loyally, you'll know that we each session we feature a fun Canadian fact, and I can't say that this photo looks that it's not invoking a lot of fun. But does anyone know who this is? I won't pause for very long because I think you will not recognize this person. So this is Madge Thurlow Macklin, and full disclosure, she's not a Canadian, but she is an American physician who was working in London, Ontario, when she made some of her major contributions to the field of medical genetics. In fact, she's considered by most to be the mother of medical genetics because she was a very strong advocate for getting medical genetics into exactly that domain, into the medical curriculum and making it a legitimate field. And shown here in the corner is one of her papers, a very important paper, New Symbols for Pedigree Charts. So some of you who have attended our clinics, you'll see us drawing these little things that looks like a weird game of hangman meets X's and O's. And so we create these things called pedigrees, or these family trees. And so she wrote this very important paper in 1930 while working in in London, Ontario. Interestingly, she was also very much associated with the whole field of eugenics, which is, trying to design the perfect human, which is an interesting but perhaps dark part of our international history in genetics. So remember, we're keeping track of all these fun Canadian facts, because at the end of the year, we're going to have a very amazing race-like contest, and someone's going to win not money. So that's our fun fact today. And this is a nice segue for me to introduce our guest. I'm very excited about our guest. You'll remember that our first couple of chats. Sorry, I'm having some headphone issues here. Our first couple of chats were very much the history of our inherited arrhythmia in Canada. We had Pam Husband and Andrew Cron, and then we started getting into some really interesting conversations with Mike Ackerman about activity. Today is a really exciting session for me to be part of, because I thought it was time to really get into the education of genetics. And so we have Melanie Care, and yes, her last name is Care for obvious reasons. She is a genetic counselor at the University Health Network in Toronto, which is a very impressive organization. They have an amazing medical genetics group, and they specifically have embedded cardiac genetics into their inherited heart rhythm program. And Melanie's been there for about 17 years. I found that hard to believe because she appears very youthful. Now, another little known fact about Melanie is that I think she might be playing the trumpet for us today, if I'm not mistaken. So with that said, I'd like to welcome Melanie to the studio, and hopefully I have stopped sharing. Evan, double check that I've stopped sharing, and I should just be featuring Melanie. Melanie, thank you so much for joining us today.
Hi, Dr. Sanitani. Thanks for having me.
That is my pager going off.
You're very high frequency tone there.
I still carry a pager, and I am in scrubs because I am doing double duty today. Melanie, welcome to the program. You and I talked about this a little bit, and our goal was really to create something that people can refer back to, because we talk so much about genetics.
Absolutely.
And I'll do a little sneak preview. We're going to talk about genetics twice with Melanie. So today we're really going to focus on understanding the basics. So let's start as basic as I know. We won't go back all the way to the sperm and the egg, because I think hopefully our audience can look that up on the internet. But let's start with DNA, and give us a little introduction, like what is even DNA?
Yeah, absolutely. Well, I think what you say is absolutely true, and it's really increasingly we hear words thrown around all the time, right? We hear about genes, we hear about genetics, we hear about DNA, but actually, I think trying to conceptualize what these things actually are is really difficult for all of us, for people in the general public especially. And so, we need to think about what are these building blocks of inheritance and genetics. And that's where we start. And we start actually, I kind of like to start actually maybe a little bit more specific than that, to speak about genes. I mean, genes are really important biological instructions for us, right, in our bodies. And so when you think about gene, how often do you hear that term thrown around? Well, if you research, or if you Google gene, what's the definition? unit of heredity. Again, it doesn't really mean much, right? I think these are terms that don't mean much to people. So I think that it's important to think about our genes as the instructions that tell our bodies how to grow and develop and work properly and continue to work properly throughout the whole course of our lifetime. Genes themselves are made up of DNA. So DNA is like the building blocks, or I think about this as a biological alphabet. Okay, so that's how I often can conceptualize this, is to think about DNA and our genetic material being an alphabet. DNA is made up of letters. Our English alphabet, our English language, has 26 letters. The biological alphabet has 4. And it is, the body reads that alphabet just the same way that we would read whatever language we speak or read in or communicate by. So DNA is these building blocks that you strung together to make sentences or instructions. That DNA comes together in a way that makes sense to our body, that our body can read and follow, that actually is an instruction about something to do. And the gene is the instruction. Does that make sense to you?
I'm staying with you so far. I'm amazed that English 26 letters. How can we do so many things with just 4 letters?
Mm-hmm.
How are they arranged? How does that turn into you and me and and Johnny and Bill and Mabel and the diversity that we see?
Well, those 4 letters, so those first 4 letters are strung into, again, it's really linear, actually. They're strung into a line, and our body reads them in triplet code. So it reads them in groups of 3. And so if you think about 4 letters, they can come in any order, but they're always read within groups of 3. And there's multiple different, now you're going to test my my knowledge here, but there's a number of different triplets that make what we call, they're called amino acids, actually. And they can be strung together in any variety of order. Every 3 letters of that code is a single word. And you can use all those different words in a code that our body understands. So we have infinite numbers of words. Our body doesn't, but the order that they come in changes the meaning of the sentence for what our body can do. So, I can think about, there might be an instruction that tells your body what color to make your hair, instructions for what color to make your eyes. There are many, many, many different instructions that are needed to make various organ systems in our body work. And it's very granular at that level. And I think sometimes it's easy to get lost in the details of that. But I think what's really important when it comes to families living with inherited or genetic diseases is to appreciate that the code is specific. The code is sending the body a message and telling it what to do. That's in the form of a gene. And our genes need to work properly so that they will follow the instructions, and our body can follow the instructions that cause us to not have specific health problems, essentially.
I think I think one of the numbers you were thinking about is 64. That's it. There's 4 times 4 times 4 options. My biochemistry degree, every once in a while I dust it off. But the amazing thing, and this is it's probably been more years than I remember, but when they finally finished the Human Genome Project, I know people were thinking, oh, humans are so complicated, there will be hundreds and thousands of genes. And then that number kept getting smaller and smaller. And I think we have less than 20,000 genes, most of us. And those 20,000 genes do all these things.
They do.
The gene, as I understand it, basically is the instructions on how to make proteins.
Yep.
And the proteins then go off and do their job. Now,
that's correct.
I'm very guilty of this, and I think all of us are in the clinical realm. And we talk about people having the gene or not having the gene.
Yeah.
But that's not really the right language, is it? Because
No,
most of us have the gene. It's just what's inside it.
Well, and that's so the question, the key question for any genetic disease, whether we're talking about inherited heart conditions or otherwise, the question really is, are our genes working properly, right? So genes do a job. That job needs to be done so that we remain healthy, that our bodies work the way that they're supposed to work. So, we talk about this a lot, yes, in that clinical context, because it's a very common misnomer to say, oh, I have the gene for, let's say, long QT syndrome. Well, but you're right. Absolutely. We all have the gene for long QT syndrome. We need that gene because the job it's doing for us in our body is really preventing us from having long QT. It's keeping our heart rhythm and heart electrical system working the way that it's supposed to. If there's a problem with that gene, that's when we can be at increased risk for health issues, cardiac issues for long QT syndrome or other inherited heart diseases, or an increased risk for developing those kinds of issues. So yes, the question is always, is the gene functioning properly? That's what we need to find out. And that's what we're always looking for when we're trying to sort of prove or identify these genetic conditions in patients that show up in our clinics.
I will go back to the sperm and the egg here. We start with just a little bit from mom, a little bit from dad, and then we have to turn it into billions of cells.
Yeah.
So there must be a way for the DNA to keep multiplying.
Absolutely.
And so is that where some of these mistakes then come from, or is it always from mom, always from dad, or do we make our own mistakes?
Yeah, that's a great question. So yeah, I think it's important to sort of backtrack for a minute. And when we talk about these genes that we have and genes that are working or not working, we have to recognize from a basic perspective that actually every gene we have two copies of, right? We inherit one copy of everything from our mother. We inherit one copy of everything from our father. So if we're talking about an inherited heart condition, again, I'll go back to long QT syndrome. We all have two copies of every gene for long QT syndrome. So we're talking about this specific gene. You got one from mom, you got one from dad. Yes, via egg and sperm cells. Those then, once fertilization happens, then all of our genetic material has to be replicated, right? Copied and split into two. And that's how you get two cells. And then those replicate again and divide into 4 cells. And then that is how, that's a big complex mechanism, right? Cell division, copying all of our genetic information, very complex. We're very lucky. Again, putting it back in that context of books, it's kind of like you or I having to sit and rewrite an entire encyclopedia without making a mistake, right? Like that's a big task. It's a big ask, actually, to do that perfectly every single time. The good news is that our body has very good editors that can come behind those of us that are doing the copying, or the workers that are doing the copying. The editors can come along and fix most of those mistakes. Once in a while, that doesn't happen. And so, yes, you can actually have a brand new sort of genetic condition in a person that happened very early in their development because there was an error that was made in that initial copying. I will say that some genetic conditions are much more prone to that. Some genes don't have as good editors, essentially. And so there are some genes that are quite commonly found to be new in an individual, and then they can be passed on from there. With our inherited heart conditions, most of the time they are inherited from a parent. The gene issue itself is most often inherited from a parent. However, very important fact I think to notice is that, or to recognize, is that not everybody that has the gene problem has a heart problem, right? So, one of the very first questions that I think a lot of people will ask me when we start talking about genetics, they're sent for, genetic assessment for an inherited heart condition. And they say, this isn't inherited. I have this problem, but nobody else in my family has this. So it cannot be, right? It's not genetic. There's no other family history. But the truth is that many of these, not all of them, but many of them, it's easier, I think, to think of them more as like a predisposition to a certain kind of heart issue, which means that your mom or your dad might carry that predisposition genetically, but never manifest evidence of it or never have symptoms related to it. So nobody checks their heart. And so it's it's really important to remember that if a doctor thinks that someone has a condition, a heart condition that could have an inherited basis, family history is important, but it's not the only piece of information to tell us whether something's genetic or not. So we have to think about it that way too.
So it gets increasingly complex once you know a little bit of knowledge and it gets really complicated. Now we've been dancing around it. We've been saying mistake or spelling mistake and things. Let's jump into I hear terms. People talk about mutation.
Yep.
People talk about variants. Let's educate our listeners. What is there a difference? What should we be saying?
Yep. Absolutely. This is and I'm sure you've experienced this too, Dr. Sanitani. This is a really evolving part of our field. I think the language that we're using to describe genetic problems that cause medical diseases, right? I think that for years and years and years, the term mutation was used. So that's still pretty common language that we hear, I think. And when people say mutation, it means that there's an abnormality in a gene. It's different from what we talked about the gene being a sequence of letters. And so a mutation would be an altered letter there. So it's like a typo, right? Traditionally, the term mutation is equivalent to bad or disease causing. So if somebody has a mutation in a long QT syndrome gene, they're expected to have long QT syndrome. When I think where that has started to change is that sort of by definition, the term mutation can mean a lot of different things, but it means any kind of abnormality, any kind of difference. But we're learning more and more that not every difference or abnormality in a gene actually causes a problem. So how do we delineate that? How do we describe what kind of things are actually going to cause a heart condition or could cause a heart condition versus what kind of variation might be nothing, right? And so that's where we get into some of the newer language that we're hearing. That in genetics, so if you were to speak with, for anyone who's spoken with a genetics professional in their recent history, would start to hear terms like pathogenic variant or a benign variant or a variant of uncertain significance. So any difference in that genetic code or any single letter change or any alterations within that, sort of any variation from normal. And normal means that we've looked at thousands of people and we look at the sequence of the gene and it looks the same in most people. That's what we consider normal. But humans are full of variation. So any variation that's found in a gene now is going to be referred to as a variant, not a mutation, but a variant. And then we put a classifier on that. So is this the kind of variant that actually impacts how the gene does its job? Or is this a variant that has no impact on how the gene does this job? And I'm going to go back to my sentence, my language sort of analogy here. And this was actually an analogy. I think it's nice for everybody out there to know. I learned from you guys too. So this is something that was used to describe back to me what I had told them. And I found it very useful. So if you look at a sentence, I always say, if you look at a sentence and it's this long and I change one letter in the middle, it's not normal, but chances are you're going to know what it says. Your brain's pretty clever. It can read right through that sentence and it still is going to follow the instruction appropriately. But if that changes in a very important word that changes the meaning of the sentence, then you can't follow the instruction anymore. So the question we always have to ask ourselves is whether the genetic variation that we found, or the variant, which is what we use now, is in a key word. Is it in a very important word in the sentence? So bear with me here for 1 second, Dr. Sanitani. I'm going to put this into an example. So let's just say you're out for the afternoon. It's a beautiful afternoon. You've got a 16-year-old and you really want that 16-year-old to go wash the car. So you write a sentence to them that says, please go wash the car. Fine. They know how to read that. They'll follow that instruction. Now let's say there was a little bit of a mistake in there, and let's just say you inserted an R in the middle of the word wash. So now the instruction reads, please go wash the car. it's not normal. It's not quite proper. It's not quite correct, but you know what to do. He or she still knows what to do. They're going to go and they're going to wash the car. They might laugh at you because you use the word wash, but they will do that. They'll be able to follow that. Let's go a different way. Let's just say in that sentence, I replace the last letter in the sentence with a T. So instead of an R, there's a T. So now the instruction actually says, please go wash the cat. That's not what you want them to do. And that's an error that's going to cause a different outcome. So those are the kind of errors that or alterations or variants that we would put that classifier as being. The terms that we use in genetics are pathogenic or likely pathogenic. And the term pathogenic means associated with causing disease. So, if it's in one of those key words, the question we always ask is the spelling change in a key word, or is it in a word that doesn't matter? Does that make sense to you?
I think so. I like the you can wash the cat, or you can wash the car, and they're very different. But wash, those are really nice illustrations of the interpretation and how that goes from a variant to a protein that a protein that may or may not work. Now that I understand that in some of the genes, especially some of the genes, as you say, some of the genes that are not as preserved, or that have they're more prone to error.
Yeah.
In some of those, 2 to 3% of the population are going to have these variants in them. And so it's not uncommon to see, people walking around who are totally normal, who have no cardiac disease, but they have these variants. And I find that a tricky concept to get around, because sometimes, one person in the family can have a cardiac arrest or a very significant event, and there will be others that carry the variant, but the variant may or may not be causative or the real important thing. I mean, all of this conversation, I feel, is setting us up beautifully for our conversation in May, where I'm going to ask you, who needs a genetic counselor? But how is it that probably all of us are walking around with some of these variants in very important places? I guess it's good that we have two copies of each.
I think this is, to be honest, I think this is still something that's kind of perplexing all of us, right? So we know that we can carry, and again, we first always have to separate like benign variation, this doesn't cause a problem, from variation in gene that causes an impact on the protein or on the job that's being done. And I come back to, truthfully, we don't know. We don't know why some people, if you've got 5 people in a family, they all have the same gene variation. We know that it impacts, we know that it's an important word. We know that it can impact the function of the gene, but you have one person who developed their heart condition in childhood, another who has some minor palpitations at 30, someone else who never developed a heart issue, somebody who showed up with some significant cardiac event at 45. So there can be that broad spectrum. There must be other things that impact and that play in here to how that gene is expressed in different people, right? So there are some of the sort of possibilities that I don't think we've proven any of them, or very many of them yet. Some of them, there are probably other sort of what I would consider sort of secondary genetic factors that people may have that actually interact with that primary factor. And perhaps some people have more of those ones that are helpful or more of those ones that are high risk. And so when you put multiple genetic factors together is when we start to see the actual heart problem manifest. There may be environmental factors that also impact how the gene does its job. Lifestyle factors, there are some of these, particularly with ARVC, I think we've started to see that there may be some impact of competitive athletic training on how the genes of ARVC are expressed. We saw a lot of people who are very competitive athletes that were being diagnosed with ARVC, and their siblings who weren't as active have the same gene finding but didn't develop as significant cardiac issues. So again, these are things that are emerging. And I think there's a lot of interest in trying to understand exactly why we see this variability within families. But the bottom line, for us is that we see it. And so we know that, just because someone has a pathogenic variant or a clear-cut abnormality in a gene, it doesn't mean they're going to get a heart condition. It means we need to pay attention to them. We want to make sure that since they're at risk, if something does start to change, whether it's in their heart function or heart rhythm, that we're paying attention to them, that we're making sure that it doesn't, doing our best, the best job we can to make sure that that's found early if something does change, so it can be medically managed appropriately and reduce the risk for serious outcomes, right?
Yeah, and you brought up, some really important points. For example, arrhythmogenic cardiomyopathy, or ARVC, is one form of that. One has to think in Canada, there's a very large population with arrhythmogenic cardiomyopathy in Newfoundland, and but it affects the males very differently than the females, but yet it's passed on by both.
And sorry, I'm going to interrupt you just for one second, because although that differential exists, you can't live in a place where, as a female, if you have this, you think you're definitely going to be okay, because we definitely have, individuals who have that common Newfoundland cause of ARVC who have significant cardiac issues. So we also don't want people to be lulled into a sense of security because they're one sex versus the other, that they're more or less safe, right, or don't need the follow-up, right? Do you know what I mean?
Right. Yeah. And Brugada syndrome is another one where, males seem to be much more effective. But again, as you point out, females can also have, severe events in Brugada syndrome.
Yeah.
So the other, this is, I'm really enjoying this sort of this, we're going into a lot of these things, and I'm reflecting on how casually we speak about some of these things. One of the things that often comes up is, especially in families that have been impacted by a sudden cardiac event, there's, well, why don't we just, as soon as the kid is out, why don't we just take a little, spot of blood when we check them for, thyroid, and just do their whole genetic panel, and then we can never have anyone die of SADS again. Why aren't we doing that? I know some of my thoughts, but
well, and I think everybody, it's an interesting question, because I also think that there are different camps when it comes to that. And I think we're going to see this evolve over time as well, like sort of what people are doing. But I think we're still in a place where you have to remember that although we have the knowledge that we actually do have the entire code at our fingertips now. We've had a lot of people that have had their entire genetic code sequenced, and we can analyze that to look for differences, variations within the code. The problem is the interpretation remains a really significant issue, right? And when we talked about briefly, we sort of touched on this idea that, first of all, there's a lot of benign variation between humans. We're not identical. Of course not. There's a lot of variation that we all carry, and understanding which ones cause a problem and which ones don't, leave us with this very giant middle ground, this gray area. There's a lot of variation in our genes that we don't understand. We don't know whether it causes a problem or not. And so if you take a newborn baby and just sequence their DNA, what you're going to end up with is a whole bunch of, they have this gene variation and this gene variation and this gene variation, but we still don't know whether that puts them at risk or not. We still don't know what that means for them. So it's not yet ready for that kind of implementation, I would say, across the, I think most people would agree at that point, although there are some that are doing it. The other thing is we've got to think about the ethical issues around this a little bit, right? You want to think about, there's a real danger of providing someone with a diagnosis based on a genetic test that may or may not be correct or accurate. And I think we need to be very thoughtful about where and when we ascribe those diagnoses to people when they're healthy. When in babies, we don't know what's coming from in terms of health for them. The last thing you want to do is start telling all these newborn babies that they could be at risk for something that is not ever going to be a risk for them, because we've misinterpreted or understood the raw genetic data that we have in front of us. So we want to be careful about that, I think.
Yeah, no, absolutely. And Mohammed Mohsin has put a great comment in our chat, talking specifically about a certain gene. Remember, we all have this gene, but we may or may not have variants within that gene. Variants are, alterations in the amino acid sequence that change or don't change the function, the protein that comes out. And CACNA1C, which is a bit of a mouthful, to do with calcium. That's one of these genes that has been implicated in conditions, but also refuted. And so a great example where there are several different diseases that are loosely associated with it, but in any family, it may not look the same as even within relatives, which is remarkable. So I agree. Like our understanding is not quite there to say, okay, we're gonna print your, we're gonna put your genotype on a card, and then you're going to the NHL, you're gonna play piano, and you sir, I'm sorry, you have to sit at the sidelines because you have a variant that we don't trust. So we may create some very concerning scenarios. And that's we opened our session remembering Madge, who was the mother of medical genetics, and her, even back then, almost 100 years ago, talking about eugenics. So we still haven't sorted it.
No,
I want to make sure we touch on one more thing, and this is a very medical kind of thing. Can you just explain for our listeners, what does it mean when we say the genetic test was negative? That it's such a, even saying it sounds so, imagine you're, saying that and we say it all the time. Is that good news or bad news? I don't even know what that means.
For sure. I mean, negative is negative. We think of, the way that we use terms sometimes in medicine is different than we use them in our regular lives, right? So, I mean, it's an important distinction. And I actually, I try to stay away from that, actually. And I think there's a lot of debate even in genetics about the term, like we talk a lot about the language that we use. A negative genetic test basically means it came back normal. When you think about a normal medical test, right, it means that we did not find any genetic alterations that we believe are of significance. Nothing in those genetic analyses that we found that we think is likely or does predispose to an inherited heart condition. And it's like opposites of what our regular language is, right? A positive is a good thing and a negative is a bad thing in regular life. In medical terms, negative means it's okay, thumbs up. Everything came back looking good. If it's positive, that's when we found something significant that we think puts you at risk for an inherited heart condition. So it's
very
tough
confusing.
because it's backwards.
Almost backwards. And thank goodness we have genetic counselors who can translate the genetic code and the variants into English that's not backwards. But I feel that the families that are out there, I still think we have a lot of work to do. And that was certainly one of my goals today, is just to start this conversation and go to some of these definitions and concepts. And I'm so glad you're going to be back next month, and we're going to really delve into the counseling side of it and some of the mechanics. And just before I let you go, Pam Husbands asked, and I don't know if she's put this in the chat just to make me squirm and potentially see if I fall off my chair, but she said, what about newborn gene testing when you have a when you have a variant in a
Mhm.
parent that is um, that is known to be associated with a disease in that family, and she could have typed in fetal. We can test the DNA in fetuses, and you can even do pre-implantation genetics, which gets into a whole other, another level of tough decisions for young people who are contemplating families. But
Mhm.
what are your thoughts? What's the short answer to the
Yeah.
impossible question?
There isn't one. There's no short answer to that question. But I think the short answer is that it depends on each individual situation. No two situations are the same. No two genes are the same. No two gene variants are the same, or rarely. The decision to test babies or children for some of these conditions depends on things like, are they at risk for serious cardiac events in the newborn period or as infants, right? So if there is a medication or a treatment that's going to be given to a baby that has an inherited heart disease, because we have evidence to show that that medication is going to reduce their risk, then it's pretty hard to advocate not to test them. It's, at the end of the day, it's still a parents' family's decision, I think. From my perspective anyway, I think these are decisions that families and parents know their job is to make the best decision for their children. And this is one of those decisions. And it's not one that everybody has to make. And it's a difficult one for lots of people. But we have to trust people to know what is best for them and for their families. Um, you know, genetics has a long and storied history of saying we won't do genetic testing in children. It's something that comes up quite regularly. It's a very traditional way of thinking. And I think in inherited heart diseases, we can't be that black and white about it. And we aren't that black and white about it, because these are not black and white situations. And so, I think it involves an important conversation with genetic counselors, cardiologists who manage these conditions. What are the implications? If I test my child for this now, what does that mean for them today? What could that mean for them down the road? When are their treatments? When do these things onset? I mean, if somebody had a child that had a devastating cardiomyopathy at the age of 1, it's hard to advocate to not test the siblings for that similar gene, right? Because we know it can present at significantly at young ages. So I think it's really important to have the conversations with people, be honest about what the outcomes could be, and so people can make those best choices. No one answer to that one.
Fantastic. Melanie, it's been an absolute delight talking to you, and I think you've given our viewers a lot of great information that hopefully Evan and Aaron are going to make this available so people can refer back to this and send this to their relatives and to their health providers. I recently resurrected a study we did over a decade ago that really showed that the genetic literacy of most people finishing medical school is very limited. So unless you're dealing with a SADS specialist, your doctor may not have any more knowledge about your genetic result than you yourself do. In fact, you probably know a bit more if you've been counseled properly. So Melanie, thank you so much for being here. And I will look forward to our part 2, and we will see you at the end of May.
Thanks for having me. Pleasure to be here.
All right. What a great conversation. And I mean, I'm very fortunate to have the ability to chat with genetic counselors, and they bring such an important perspective to what we do. And today we didn't even talk about the partner that goes with the genetics is the phenotype. The phenotype, of course, is the expression of these genetic variants in the individual. So it's always about more than just what the variant is. So with that said, I think we're at time, and I've really enjoyed having this conversation with Melanie today, and I hope you've found it helpful as well. As I say, we're in the middle of exciting times at the Canadian SADS Foundation. We're stepping back and rethinking everything. We're touching back to our roots and our mission and our vision, and really want to make sure that there are not people out there who are affected by SADS conditions that are suffering in silence, or don't have access to good information and knowledge, because this is a rare part of healthcare. It's not the front page, except when it is the front page. So we hope that we can be of service. So thank you so much for joining, and I will see you next month. I will do something. Well, maybe it is in character. So last month, Mike Ackerman kindly gave a shout out to my daughter, who had matched for a residency in Denver. My other daughter got engaged between that last session and this session. So that's been very exciting news in our household, and ensures that I will have to keep working well past the age of 70. But that's been wonderful news. And so both the daughters are in a great place. So thanks for having me in your day today. Bye-bye.